If you sit next to a river and watch it flow day after day, it's natural to wonder, how can it continuously flow? There's this giant torrent of fresh water, watering all of the plants, watering all of the animals, ultimately allowing life to flourish, and it just flows without end. How is this possible? Of course, it's the rain, right? The rain is what powers all of the rivers. But what powers the rain? The sun. Like so many questions I've asked in these videos, it really goes back to the sun. The sun provides the energy to take salty liquid water into fresh water vapor up in the sky. And then that rains down to power our rivers. You see, it often takes energy to change the phase of matter. For example, when you change it from liquid water to water vapor. That's what we're going to be learning about in this lesson, the energy needed to undergo these sorts of phase changes. Let's learn. Let's begin by reviewing our lesson objectives. First, we'll explain how phase changes relate to energy. Then we'll introduce heating curves, and lastly, we'll calculate the energy required for phase changes. Here we have our four phases that we looked at in our last lesson: solids, liquids, gases, and plasmas. Now, if I take all of the energy out of a substance, that is, I cool it to absolute zero, what phase will it be? It will be a solid. And that's because there's attractive forces that hold atoms and molecules together. They naturally want to be next to each other. So it's really important to remember that attractive forces hold molecules together. And if I want to separate the solid to a liquid, or pull apart a liquid to a gas, or even more extreme, take apart the atoms in a gas to make a plasma, that takes energy. Separating molecules takes energy. So as I go from solid to liquid to gas and then to plasma, I have to put in energy just to get those phase changes to go. That's independent of the energy I have to put in to increase the temperature. It just takes energy to separate molecules. So for example, even when this pot of water is already at 100 degrees, I still have to keep the flame on to keep it boiling. If I turn the flame off, it will stop boiling. So the energy from that flame is going directly into separating molecules. Let's take a look at a heating curve, which is a useful tool to understand these things. We're going to put on our x-axis heat added. So we're thinking about how much heat has been added by our flame in joules to this pot of water. And on our y-axis, we'll put temperature in degrees Celsius. Well, our pot of water, assuming it starts at room temperature, is going to start at about 22 degrees Celsius. When we start to add heat to it, what's going to happen? Well, you guessed it, it's going to warm up. So we draw a line going upwards to show its increase in temperature. That temperature is going to increase for a while. Where do you think we'll see a change in behavior? We'll see a change in behavior right at 100 degrees Celsius, because that's where our water starts to boil. When that happens, our line will go flat. Why is that? That's because the temperature of the water will stop warming up. Even though we're adding heat to it, all of that heat is going to boiling the water, and none of it is going to warming it up. And that line will just continue flat all the way until all the water is boiled. So the heat added to a pot of water, once it's boiling, all it does is help separate the water molecules. It doesn't warm it up at all. What all these flat lines mean is that even as water is boiling, even as we're adding heat to it, the temperature of the pot doesn't increase. It just stays the same. It sits at 100 degrees Celsius until all the water is boiled away. Now let's look at the opposite of boiling. Here we have some delicious iced tea. Do you like sweet tea or unsweet tea? I myself live in the South, but nonetheless prefer unsweet tea. I know. Anyway, I digress. The point is, this is actually the opposite of boiling. Not because there's ice in some liquid, but because of the little droplets on the surface of the iced tea. This is called condensation. And it comes from the air around our tea being full of water vapor. We call it humidity. And when you put something cold, like iced tea, in a humid environment, it naturally condenses that humidity onto the surface of the glass. And as that happens, it warms up our tea. Condensation warms things up. Why is that? Well, it's because combining molecules gives off energy. And so when the gaseous molecules combine to form liquid on the surface of your tea glass, it actually increases the temperature of your iced tea. This is just the opposite of what we saw previously. As we go from right to left here and combine things, that's going to give off energy. And so condensation warms things up. But the question is, how much does condensation or boiling warm things up? Well, for water, this is the number. Okay, what does this mean? We have 2,256 joules per gram. That means that if we want to boil a gram of water, it will take 2,256 joules. Or if we condense some water onto, say, the surface of your drink, it will warm up your drink by 2,256 joules for every gram of water that condenses. We call this the latent heat of vaporization. All right, let's give you the long definition for this. The latent heat of vaporization. It's the energy required to change a substance from liquid to gas. Okay. Here's a table of substances with different latent heats of vaporization. It's important to realize that different substances take different amounts of energy to boil. So helium is very easy to boil, just 20.9 joules per gram, and that's because helium doesn't have very strong attractive forces, while water takes 2,260 joules per gram to boil because of its very strong attractive forces. Other phase changes, though, like say melting an ice cube, also take energy. How much energy does it take to melt an ice cube? Well, 334 joules for every gram of ice you have. This is called the latent heat of fusion, which is kind of a funny name, but the latent heat of fusion is the energy required to melt a substance. Let's put these numbers to use and solve some problems. This problem says, how much energy does it take to boil a pot of water with a mass of 1,450 grams? Water has a latent heat of vaporization of 2,256 joules per gram. Notice in this lesson so far, we haven't actually given you an equation. Well, in your notes, you should find an equation you can use, but we're going to just solve this problem as a unit conversion. Let's take a look at how to do that. We know we're starting with 1,450 grams. And we know that we want to go to energy. So what unit are we going to? Well, we're going to be going to joules. So we actually have all the information we need just to do this as a conversion problem, because we know that there's 2,256 joules per gram. So we're going to cancel out gram and we're going to go to joules. Up top then, we're going to put 2,256, and on the bottom we'll put 1. When we multiply those numbers together, grams are going to get canceled out and we'll be left with joules. So you can see how this is just a very natural conversion problem to do. When we multiply that, we're going to get a pretty large number. We get 3,271,200 joules. And of course, we want to round that for sig figs. And when we round that for sig figs, because our mass has 3 sig figs, we'll want to keep 3 sig figs here. So 327, and then we'll add our place-holding zeros to make that number just about the same. So it takes 3,270,000 joules to boil a pot of water with a mass of 1,450 grams. Okay, now we'll solve a problem using our equation. This one says 13.6 grams of water condenses on a cold glass of tea. How much heat is released by this water as it condenses? Water has a latent heat of vaporization of 2,256 joules per gram. Well, the equation we can use says that Q is equal to mass times the latent heat, in this case, of vaporization. You can just substitute this, by the way, and have fusion. If you get rid of the V and you put F, then that's the same equation that we have for fusion. In this case, though, we'll keep our V because it's for vaporization. So let's put that V back on there. Boom. Okay, so let's go ahead and calculate the amount of heat. Q stands for heat, as we've seen previously. And we do mass, which is 13.6 in this case, times the latent heat of vaporization, which is 2,256. And we simply multiply those together. And when we do that, we'll get 30,681. So you can see this is exactly the same steps as if we had used it as a conversion, where we're just multiplying the mass by the latent heat of vaporization. We need to round for sig figs. Here we should be left with 3 sig figs. So 1, 2, 3. That 6 is going to round up, and we'll get 30,700 joules. Now it's your turn to give this a try. An ice cube at 0 degrees Celsius and with a mass of 25 grams is placed in room temperature water. How much energy does the ice cube absorb before it melts completely? Water has a latent heat of fusion of 334 joules per gram. Okay, pause the video and see if you can calculate the total energy that is needed. All right, were you able to get the answer? You should have gotten 8,350 joules of energy. Let's review what we've learned. First, we explained how phase changes relate to energy, where we said that molecules have attractive forces holding them together. So it takes energy to pull those apart, and it gives off energy when we bring them back together. Then we introduced heating curves, where we saw that it takes energy to warm substances, and then energy to change their phase. And during that time, they don't change in temperature. Lastly, we calculated the energy required for phase changes.
Hey, hey.